So this is Weinberg with Matheus, Ferreira, and Hourigan. I'm not sure if Matheus is here in the audience. Anna and Kathy who are here, and Matt who's also here in the audience. So a quick overview of what we expect in this talk. We developed methods to compute optimal selfish mining style manipulations in cryptographic self-selection proof of stake protocols. So technically, this involves reducing our problem into an MDP with uncountably many states. These states are going to look like real numbers. These numbers are going to mean something. Interestingly, getting net-zero discretizations of this MDP and solving a Bellman equation on it is not even an unbiased estimator on the reward we want to calculate. So instead, we develop practical simulations with provable guarantees on the rewards of a strategic proposal. So this is an overview on the talk. So before we unpack the details, a bit of background on blockchains. Blockchains are what are essentially distributed ledgers. It's a ledger because it's an append-only data structure. There are transactions that keep happening all across, and they have to be added to the end of this ledger. It's distributed because there are proposals sitting all across the world, throwing in their bit to maintaining this ledger. The challenge is to make sure all these proposals are in sync with respect to the contents of the ledger. So most blockchains tackle this challenge through a typical idea. They run a leader election protocol, and the winner of this leader election protocol gets to attach a block to the end of the ledger. Of course, proposals are not going to do this out of charity. They have to be rewarded for proposing blocks. And as soon as the reward comes into the picture, proposals want to optimize the rate of getting rewarded. In other words, the rate of getting elected. So a simple manipulation that the proposer can perform is something called a Sybil attack. So here, a single proposer can pretend to be multiple entities and participate in the leader election protocol. And Sybil resistance says the protocol must be resistant to sending a bunch of millions and increasing the rate of it. So there have been a couple of predominant Sybil resistant protocols that have been around: proof of work and proof of stake. Most modern blockchains like Algorand and Ethereum post 2022 have adopted proof of stake. Here, proposers are to be elected proportional to the stake that they hold in the cryptocurrency or the network. And as well as we expect people to make some kind of investments into the network, along with Sybil resistance, we also have to guarantee fairness. That is, the probability of getting elected should be proportional to the stake that every proposer has invested into the network. All right, this wraps up the introduction part. So we will now dive into the cryptographic self-selection protocol, which we are going to try and manipulate later on the talk. So this is going to happen in rounds. So each round T, we are going to start with a random seed QT. This is going to be a number between 0 and 1. How do we get this? We'll do this inductively, so hold on till the end of this round. But however, once we have the seed QT, this is announced to all stakers, like all owners of coins in the network. So I am a coin owner in this network, and I clear this seed QT. I'm supposed to do the following. For every coin that I own, there is going to be a verifiable random function attached to the coin. And I would want to evaluate this VRF of each of my coins at the seed QT and broadcast these outputs into the network. So we'll unpack what a verifiable random function is. As the name suggests, it's random. So you take a particular coin and it has its own VRF. Computing and evaluating this VRF at a given input X should be possible only to the owner of the coin, not by anybody else in the network. And further, without actually evaluating this VRF at an input X, and for the rest of the network who can't even do this evaluation, the output should not be predictable. That is, it should look like a uniform graph between 0 and 1. So this is the random part of verifiable random functions. Now for the verifiable part, remember only the owner of a coin can evaluate the output of this VRF at any given input. So the owner can potentially just lie through its teeth, right? So verifiability says that is not the case. Given an input X and an output Y, checking whether the VRF of X is actually equal to Y should be possible by everyone, not just the owner of the coin. Okay, so I think we are almost done. So all we need to do is, okay, there are going to be a bunch of these outputs of VRFs that are floating around. We look at the coin with the smallest output, and the owner of this coin is selected the leader for this round. Because the output of VRFs are going to be like a uniform cross between 0 and 1, it is equally likely for each coin to have the smallest score. So every proposer is elected proportional to the number of coins that they own. However, this is extremely inefficient in the sense, if I own a bunch of coins, I'm supposed to evaluate the DRFs of all my coins, and the worst part is I have to send all of this over to a network, which is going to cause a lot of strain. So we'll improve this slightly. Instead of attaching a VRF to every coin, we'll attach a VRF to every wallet. So same as before, if I have a wallet and I have received QT, I evaluate my personal VRF at QT and broadcast it into the network. However, I can't elect the wallet with the smallest output because there are different wallets that are going to have different stakes, and wallets with a higher stake will have to be elected much more frequently. So that's why something called a scoring function comes into the picture. The scoring function takes in the output of a VRF and the stake held by every wallet and outputs a score to each wallet. And we pick the wallet with the smallest score to be the leader of this one. Indeed, we like to guarantee fairness and civil resistance. Fairness translates into the probability of a particular wallet having the smallest score must be proportional to the stake held by the wallet. Civil resistance translates into the following. So instead of having all your stake in a single wallet, if you split it across a collective of wallets, then the probability of having a small score should not increase by splitting your stake across, right? So a side result that we have is if a scoring function is fair, then it also has to necessarily be civil resistant. Due to interest of time, I'll skip delving into the details, but if you're interested, I'm happy to talk about this offline. Okay, so where are we right now? We begin with random seed QT. Every wallet computes the VRF and broadcasts a lot of nice stuff into the network. And the wallet with the smallest score is elected the leader. All that remains is to transition into the next round, for which we need to pick a new seed QT plus 1 for the next round. And how do we do this? Remember that the output of this VRF, we'll be calling credentials from here on. So remember that the credential looks like a uniform draw between 0 and 1. So we'll leverage that as the source of randomness. The wallet with the smallest credential, the credential of the leader is the seed for the next round. So that is going to be the seed QT plus 1 for the next round. Alright, so that is the self-selection protocol. So given this, our result is going to look like the following. For a particular fraction of stake alpha held by a wallet, our methodology gives a tight bounds on the optimal reward a proposer can get by being strategic. So for that, we first need to set up the strategy space for the proposer, which we'll borrow from Ferreira et al. 22. So we'll borrow some numbers from Algorand and we'll make up some numbers around this. Alright, so suppose I'm the proposer and I'm trying to be strategic in Algorand. Blocks are made every 3 seconds, and we pretend, in the first second, like all these exchanging of VRFs and scores and all those things happen. So I want to hold on to giving out information about me for 1 full second and try to learn as much as possible in that second. So what can I look to learn? So for 1 second, based on my internet connectivity, there are going to be a bunch of honest wallets B whose credentials I will be able to learn. And my internet is not going to be perfect, so there are going to be a bunch of other wallets C whose credentials I will not be able to learn. So that is, I'm going to learn stuff for 1 second, and then I'll decide whether I want to broadcast my credential or I'll want to be I'll pretend to be offline and then just hide my credential, right? So this is just 2 actions, not a lot of flexibility, but I can take this 1 step ahead. What I can do is I can split my stake across infinitely many wallets with negligible staking on each of them. Civil resistance says this does not increase the probability of me getting a smaller score. I'm fine with this. However, I'm going to get flexibility out of my second smallest score, my third smallest score, and so on. So in this example here, so I have 3 credentials with very tiny and very similar scores. Alright, and if I hide 2 of them and broadcast any one of these 3, I'm very sure that I'll end up winning this round. Right? Because I have super small scores, it's unlikely someone is going to outscore me. So I can stop worrying about this round and I'll start thinking about winning the next round as well. So how do I do this? So in this example, so suppose I broadcast credential 1. Alright. I can compute the hypothetical seed for the next round, that is just credential 1. So given the hypothetical seed for the next round, I can compute all the credentials of my wallets for the next round, I can compute all the scores of my wallets for the next round. So here I actually find my smallest score for the next round is 0.1, which is kind of large. I am very sure that I will lose the next round. On the other hand, if I broadcast credential 3 and hide the first 2, I'll do the same exercise. I'll compute the hypothetical seed for the next round, I'll I have compute hypothetical credentials and scores for the next round. I have two wallets that follow with extremely small scores. Well, then why would I want to broadcast in first or the second credential? I would rather broadcast in third credential and give myself a shot at winning this and the next round. Okay, why would I want to stop with the next round? I can say, okay, conditioned on winning this round with credential 3, conditioned on winning the next round with credential 2. What are my scores for 2 rounds after? Why stop there? 3 rounds after, 4 rounds after, all the way down to an infinite partition. There is something else also that I can do. Remember, I collected all these honest credentials at the start before I broadcast my information, right? So what I will say is, okay, I'm going to hide all the credentials. Of course, I'm going to lose this round. But if one of these credentials and wallets in B end up winning, I know I have really small score for a succession of rounds. If that is the case, I can even consider sacrificing this round and get compensated in future rounds, right? All right, this is the strategy space. So now we will get into the simulation part of the problem. So what is the goal? The goal is to find the optimal fraction of rounds a strategic proposer can end up winning, right? So the first challenge is that when we are looking at fraction of rounds 1, which is hard to get a handle on, it would be nice if we had a total rewards version rather than a fraction of rewards problem, right? So we convert this into a total problem using a trick by Sebastian et al. In interest of time, I won't get into the details, but I'm happy to talk offline about it. For the rest of the talk, pretend that the proposal is trying to optimize the total number of rounds. Of course, this doesn't make sense because we are looking at an infinite game, so the proposal is going to win infinitely many rounds. But just hold on with it. Just pretend it's the total number of rounds, right? Okay, so we find and convert this into a total problem. Now we restate this as a fixed point computation problem, which is a little more easier to handle if you are trying to run simulation. So if I have a proposal, what do I see every round? For each of my credentials, there is a tree of credentials, a tree of an uncountably large tree of future hypothetical credentials that grows below every credential, right? Given that I want to optimize my expected current rewards, it makes sense to summarize this infinite tree as like expected future reward below every wallet. So once again, if you look at this example here, I look at credential 1. So suppose the expected future rewards from broadcasting it and condition on winning the round with this round with credential 1 is 0.3. And suppose like now, because I know my credential, I can also compute the probability with which a wallet in C whose credentials I do not know will outscore credential 1. Alright. So I know the expected future rewards, I know the probability with which I won't win this round if I broadcast credential 1. I have sufficient information to compute my current rewards if I broadcast credential 1. So how do I calculate it? It's going to be 0.95, the probability that I won't be outscored, times 1 plus the 1 because I end up winning this round, plus 0.3 the expected future reward. Alright, I know the numbers doesn't make sense because we are pretending the total rewards is what we are looking at, but hold on. Okay, now that I'm trying to optimize my rewards, what do? I look at each of my credentials and then say what is the expected reward from broadcasting this credential. I would broadcast the credential that optimizes my reward. Alright. So I can write a fancy function for this. We'll call this function f that takes in as rewards all of my infinite credentials and all of the expected future rewards. Alright. And what is this going to output? This is going to output the expected current reward given these rewards and credentials. In particular, if the input to this function f comes from the distribution of an optimal proposer's rewards, so we are trying to simulate an infinite game and we have just simulated one round of this infinite game. So an infinite game still remains, so the output should also be the same distribution as the input distribution of rewards, right? So in some sense, we took this function f and converted it into an operator on distributions, right? The input has to be a distribution d1, the output is a distribution d2. We want to make sure that this function f, like the distribution we are trying to find, is a fixed point to this operator on distributions f. So as every fixed point problem ever, what we do is we start at an arbitrary distribution d0, the fixed point at 0, and we keep iterating until f converges. And finally, if this converges to d star, then it's going to be the optimal proposer's distribution of rewards. We want to find expected value of d star. So there are a bunch of challenges here in the sense, each round you have to look at infinitely many wallets, you have to iterate all the way down to infinity. I'm happy to chat about all these challenges again offline. However, I will just run through one representative challenge, which is this challenge of sampling. So what is one sample you are going to look at? Now, how would I want to compute the sample? Right? So for one sample of current rewards, I will have to draw once for expected future rewards for all my infinite wallets. I have to sample once for each of my wallets, and I have to sample one credential each for my infinitely many wallets. I'm going to take the maximum. So for these infinitely many samples, I'm going to take the maximum, and that is going to give me one sample for current reward. And I have to repeat this infinitely many times if you want an extremely accurate operator to compute one round of this iterated convergence, right? Well, I can't do an infinite simulation in this sense, so I'll have to settle with finite sampling. So for a large enough finite number of samples, let us look at a new operator capital F, and then we'll do the same iteration and then let this converge to a distribution D prime. Alright. Of course, indeed, expected value of D prime is going to be expected value of D star, so all you have to do is take sufficiently many samples so that the variance is small and my simulation works good, right? Turns out that is not the case. It turns out as soon as we start working with finitely many samples, we also start introducing some kind of a bias into this iterated convergence operator. So if you want more intuition of why this bias starts creeping in, I'm really happy to chat offline. There's a really nice toy example that I would like to take going over. So, but here what we have to do is, along with the concentration inequality style saying, oh look, the variance style problems are not large, simulation works with high probability. We also have to get a good handle on the bias that we introduced by finite sampling. So I'll conclude with the results. So the orange curve here is the upper bound on the optimal proposer's rewards as given by Ferreira et al. We significantly tightened it with the blue curve here. So the following can be concluded from the blue curve. For any alpha, any fraction of state greater than 0, the proposer gets strictly larger than alpha fraction of rounds by being static. On the other hand, life is not extremely plumb anyways. Even for a 25% state, which is extremely significant, the marginal fraction of rounds won by the proposer is actually quite close to 0. So even though the proposer gains by being strategic, it is not quite a lot. So this is going to be a recap. So we designed practical simulations, provable guarantees for strategic rewards. Thanks a lot for listening. I'm happy to take questions.